Hello, my name is Jason Linville. This lecture is on trace evidence, part one of two parts. And this lecture is being recorded for JS 110 Introduction to Forensic Science at UAB. We're recording this in October of 2017, fall semester of 2017. So if I mention anything about 2017, which is not going that well, then just ignore all that information and focus on the important material, which is trace evidence. In fact, just a couple days ago, John Oliver put out a piece about the faultiness, that's not the right word, the fallacies of forensic science, the mistakes that forensic scientists have made in the past. And there's an old 2009 report that brings up some of this information. And I try to hit on it some throughout this course, and I'm hoping that everybody taking this course has a better understanding of forensic science once it's done. Anyhow, let's go ahead and get started on trace evidence. The reason this is divided into two parts is this first part is going to contain some information, and I think we can go to the next slide here if I can figure out how to get to the next slide. A little bit about microscopy, because microscopy doesn't mean that it's not like if you're using a microscope, it's trace evidence. There's microscopy in a lot of other areas as well of forensic science, firearms and drug chemistry. But here with trace evidence, there's a lot of microscopy involved, so it's sort of a good place in both the textbook and in the lecture to talk a little bit about the microscope. And then we're going to talk about collecting and using trace evidence in this first part. And then it's really in the second part where we're going to focus more on specific types of trace evidence. Now, what we need to understand about trace evidence, in this first lecture, is we want to go through a case sample. Now, you guys just came off in the fall of 2017, you just came off of a mock case quiz. So hopefully that gave you some ideas of what these story type problems are going to be. And a couple of these are going to turn up on the exam in a couple weeks from now. All right. So a couple of the cases that we have described in the chat room is one describes, let's see if I can get my pen going here. One describes a teenager breaking a window to burglarize a home, and there's traces of glass on his pants. So let me see, where's my mark? There it is. Okay, so if we have a pair of pants here, okay, and in the cuffs here, I don't know why he rolls them up. Okay, there's little pieces of glass. Okay, the officer arrests the guy with the pants, and they find glass in his pants, and so this gets collected as evidence. All right, everybody, answer in the chat box or shout out loud if you're at home, or quietly if everybody else is asleep. Is the glass collected from the pants as evidence? Would that be our known sample or our unknown sample? All right. The second case that we describe is where we find a body. Why am I having difficulty finding this little cursor here? We have a body that is covered in purple carpet fibers. No, Dr. Linville, don't try to turn this into purple. Okay. Oh, there we go. All right. In which case, the purple fibers would be collected from the body, and they would also be the correct answer that everybody's giving. These would be the unknown samples. Okay, so we have our carpet fibers, which would be unknown, our glass, which would be unknown. All right, now here's the thing, okay, because we've done forensic analysis in this class. We're trying to identify blood as blood, or we're trying to identify semen as semen. And then we've also done some work with trying to determine where something came from. Specifically with DNA evidence, you want to know who it came from, okay, or where being the person. All right, here with trace evidence, it's similar to DNA where we always want to know where it came from. And what we're going to find in this first part of this lecture is you're always trying to link people, places, and things. We talked about this with the crime scene investigation. Okay, so here for the glass, what would be the known sample that we would compare this glass to? Can anybody throw that in the chat box, or again, think of this by yourself? What would be the known sample we would compare it to? Because it's not like with blood where, we're just going to compare it to glass to find out if it's glass or not. No, we're collecting it, we're looking at it, and we know what glass looks like. We're saying, yes, this is glass. But what would be the more specific known sample? Because again, we don't want to just know if it's glass or not. We want to know where it came from. And again, given the situation and Jacob has the correct answer, maybe because he remembers his example the best, it would be the broken window from the crime scene. So we're trying to link the person, okay, the suspect that we recovered the evidence from, to the crime scene where the broken glass is. So we start comparing the glass from the pants to glass at the crime scene, and we start comparing traits. Okay, again, in the chat box, I want you to list some traits of glass. Okay, what could we compare between that fragment of glass that we recover from the pants and the glass at the crime scene to determine if they're the same or not? I mean, some of these are going to be obvious. Some of them are going to be a little bit more difficult. Okay, thickness is one, color is one, very good. Glass can be thick or thin. Glass can be clear or green or even have a tint to it. All right, some other stuff. The transparency, yeah, it can be opaque. All right. We can use some instrumentation to determine like the way light passes through sort of the what's called a refractive index, some optical properties. So all of these properties of glass we can compare between the unknown and the known. All right, now let's say all of the traits that we list here and all of the traits that, again, we'll find out more in part 2. Yeah, and Jacob brings up like the minerals of the glass, the specific components. Let's say they all match. Okay, what is going to be our conclusion? Is our conclusion going to be that the glass definitely came from the window at the crime scene, it maybe came from the window at the crime scene, or it definitely did not come from the window at the crime scene? Well, we have too much to match to say definitely no. All right, and we have a couple, yeah, you guys are correct. It's maybe. And the thing about trace evidence is with all these class characteristics that we compare, we're really not going to find any individual characteristics with trace evidence. So it's always going to be a maybe answer. Because with that glass, you know, if the pane of glass that was broken at the crime scene, if it's like a window pane that anybody can buy at Home Depot, or to jump down to the purple fibers, which is what your assignment is going to be over, if those purple fibers that are found in the suspect's van or wherever it was mentioned, well, that carpet can be bought by other individuals as well, right? It's not specific to that one car. So it's always where we're comparing class characteristics. And since it's rare to find any individual characteristics with trace evidence, it's always going to be a maybe answer. And you may think, well, why even do the analysis? Because eliminating, if the traits are different, you can say it's definite no, and that can become very valuable in investigation. Okay, so that's sort of what I want you to be thinking of when you see these trace evidence questions come up as those mock case. Just know that if everything matches, it's going to be a maybe, but if there are some differences that aren't explainable, all right, then you can say definite no. All right, let's start and let's look at an overall of trace evidence. What is trace evidence? You know, I mentioned some things like glass and fibers, and really trace evidence is everything that doesn't really fall into another category. I mean, even things like a lipstick or cosmetics, oftentimes they'll go to a trace evidence section because it's not as though you're trying to identify the type of drug it is or something. It's just a basic where you find, lipstick on a shirt collar at the crime scene on the victim, and you're trying to trace it to the lipstick from your number one suspect, okay? That's just 2 items, and you're trying to gather all the class characteristics you can to determine whether it might have come from that source or whether it did not come from that source. The other thing is if you get a maybe answer and it turns out the material you're working with is extremely rare, then that could still be very helpful to the investigation. You know, if it's a rare lipstick that you can only purchase at the finest lipstick stores, I don't know. Anyhow. All right, so trace evidence analysis, as I said before, uses microscopes and other instrumentation, but it's important to understand that other sections also use microscopes. So for this microscopy discussion, okay, it just happens to be here in trace evidence. Okay, who does trace evidence? If, you know, somebody killed me and ditched me in the woods and I was covering purple fibers, that would probably catch the eye of the investigators and they would want to have those fibers analyzed. But in Alabama, at the Alabama Department of Forensic Sciences, they do not have a trace evidence section. They used to, but several years ago, they cut the trace evidence section because they realized that there were not enough cases where trace evidence was collected to justify, employing full-time trace evidence analysts. But that doesn't mean that those fibers would go unanalyzed in Alabama. What they would do is they would package them up and they would contract with either a private lab, or they would get the assistance of the FBI, some federal lab, where they would pay this other lab to do the analysis, essentially. So it's a way where you don't have to fund the section yourself for 12 months out of the year, but if a case does come up, then you send it to another forensic scientist for analysis. Okay. Some states or labs will have individuals that do trace evidence. Sometimes they'll have a trace evidence section. Like I know there's one in North Carolina. I think the North Carolina Bureau of Investigation, one of our former graduates, works for them in the trace section. So they have their own trace section there. Sometimes labs will do certain types of trace evidence, but they'll assign them to a different section of the laboratory. So in other words, they'll do fiber analysis of like carpets or other textiles, but they'll have somebody in the drug chemistry section do it, and somebody who knows how to use the FTIR and the other instruments that you can use to analyze fibers. That way, you're hiring somebody who does drug chemistry full time, and they're contributing to the lab by doing their drug chemistry. But if in that rare situation you do get trace evidence coming to the lab, then they can also help out with that. Okay. Similarly, if you have hair that needs analyzed, but for some reason you can't get DNA out of it, maybe there's not a root, but you still want to do the hair analysis, maybe it's pet hair, some type of animal hair analysis, then occasionally you'll have individuals trained in the forensic biology section to do that. I have to say that it's probably rarer for this to occur where you give individuals in a section different things. I mean, usually if you're a drug chemist, you're doing drug chemistry full time, and if you're in the biology lab, you're doing DNA analysis and serology full times. Okay. So some labs will have that trace section, but like Alabama, a lot of states will just contract out because, again, it's rare that you'll find trace evidence, and even if it's found, it has to be a situation where you know it'll contribute to the case. Excuse me. All right, so let's look at some microscopes. Now, we're going to look at two categories of microscopes, compound and stereo binocular. And then we're going to look at some specialty microscopes that really falls under one of these two categories, okay? But all of these microscopes pretty much just allow you to see more details or to better measure optical properties if you want to look at broken glass or fibers a little bit more closely. So they can be, it's not just zooming in on an object, but sometimes you know, with a polarizing light microscope, you can do different things and measure different traits that you can't just see with the naked eye. All right. Now, like I said, we're going to look at two categories of microscope, and each category is going to be associated with one of the bold terms in each of these bullets. Okay. So first, we want to go over the different types of objects you can look at, light used, etc., etc. All right, and then I'll assign them to the proper microscope. All right, the first thing that I want you to recognize is that the object that you put under a microscope can be a 3D object. That means like a bullet or a thumb or what else would you look? A fingerprint. You may want to zoom in on a fingerprint. Look at the veins on marijuana leaves. We'll talk about that with drug chemistry. Any object that you just sort of throw under a microscope and then zoom in on, that's a 3D object. Okay. There are other types of samples like hair that you could mount on a microscope slide, sperm cells definitely that we already talked about, the Christmas tree stain test, and some other materials, you know, maybe small pieces of glass, maybe not, where you can actually mount them on a microscope slide and observe them as they're mounted on a microscope slide. So it's sort of like a very thin section of an object. Okay, it's still, I guess, technically three-dimensional, but it's sort of where you're making it thin enough where it's almost like it's two-dimensional. All right. When you put an object underneath the microscope or a microscope slide, you can either look at the surface of the opaque object, meaning the 3D object, you're looking at the surface, Or you could look through transparent objects, and this is also sort of true for very small objects. So like you could sort of look through cells, you can look through fibers. If you mount hair on a microscope slide, you can actually look through those objects. And you can get more information, again, by looking at it under the microscope than you can with just the naked eye. All right. You can also use two different types of light with a microscope. All right. One is reflected light. This is, I guess, normal light, where if you just shined a flashlight on an object in order to see it a little bit better, the light comes from above the object, bounces off the surface of the object, and then goes into your eyeballs. All right. Transmitted light is something where you shine it through an object. Okay. So do you see that we're starting to associate, you know, the inside of the transparent objects with transmitted light, and you know, notice these bold terms actually line up with each other. Okay, so let's apply them to a microscope. The first thing that we're going to look at is a stereo binocular microscope. So again, this is one of the general two categories of microscopes, and this microscope is more or less like a fancy magnifier, where you're just going to zoom in on an object and look at the surface closely. So you can put any 3D object, where's my mouse? Any 3D object you can put under this microscope. You can put your thumb, you can put a bullet, you can put a fingerprint, although fingerprint I guess is kind of two-dimensional. You can put a rock, you can put a chunk of glass. So any object that you want to just look at a little bit closer can go under the stereo binocular microscope. When you put the object underneath the microscope, you're going to be looking at a surface. Okay, this is not made for very tiny objects where you want to shine light through them, like hair or fibers or sperm cells, and look at the insides. Okay, that's not this microscope. This is just zooming in. In fact, you'll notice the lens here kind of looks like a camera lens, and you can think of a stereo binocular microscope almost like a camera, where you can just put it over an object and then zoom in on the surface of that object. Okay, the type of light that a stereo binocular microscope uses is reflected light, where right here it has a little flashlight right there that's going to bounce off the object and go up and into your eyeballs. Okay, you can also use big external lights if you want. Okay, how's that for an external light that's going to shine, you know, just big sort of copy stand lights or big lamps that you can just shine on there to get as much light on the object as possible. Okay, so that's reflected light, where it comes from an outside source, bounces off the surface of a 3D object. All right. When do you use a stereo binocular microscope? Well, you can use it to search items for, or search larger items for small items. So if you're searching clothing for small fibers, then you can sort of run it, or hairs, you can run it under there. And then also you can use it as your analysis microscope for 3D objects. Again, if you're trying to match up paint chip layers, if you're trying to look at the striations on a bullet, marijuana identification, I mentioned some of these. If you're just trying to measure sort of the length of fibers, then that's something that's a little bit easier to do under a stereo binocular microscope. Okay. The second category of microscope is a compound microscope. And a compound microscope is where, notice, you'll look at a microscope slide or transparent object, but it's usually mounted on that microscope slide. You'll be looking through the object, and you're using transmitted light. Okay, so in other words, a microscope slide typically goes right here. You can't really see that purple very good. Let me try to change this to green. All right, so you have your little microscope slide right here. All right, and because it's so thin, all right, you shine light through it, and it goes up there to your eyeball. All right, and you're using transmitted light. So the transmitted light knows that the light is not up. You can't just put a big lamp right here and shine it on the object. It has to be directly underneath the object so it goes through the object. Okay, you need something transparent, like something on a microscope slide. Okay, what I want you guys to note about the difference of these compound and stereo binocular microscopes is the magnification is going to be a little bit different. All right. So looking at the surface of a bullet, you know, you want to zoom in on it. But if you want to look at the inside of a very thin fiber, like, you know, thinner than a pin, obviously, or a thin hair, or a tiny glass object, or sperm cells, which are extremely small, you need very high magnification. To get that high magnification, notice that the lenses are extremely close to where the microscope slide is. All right. And that's because in order to increase your magnification, like with the stereo binocular microscope, you may be able to get up to like 20 times magnification, 10 in the objective and 10 in the oculars. All right, here with the compound microscope, you can get up to 1,000 times. But to get that high magnification, you need your lens to be very close to the object that you're magnifying. Now, if I'm looking at a 3D object like my thumb, the problem is I'm looking at the surface, right, and using reflected light. If I get that lens too close to my thumb, there's no room for me to get that light in to bounce off the surface of the object. And I can't shine it through my thumb because my thumb is opaque, so the light wouldn't get through there. Okay, the fact that I'm looking at things mounted on a clear microscope slide and that they're very tiny and that I'm able to shine light through the object, that means I can get that lens very close to the object and I can get a much higher magnification. Okay, if I'm looking for sperm cells, I can't just throw a piece of fabric underneath a stereo binocular microscope and zoom in until I can see the sperm cells. Okay, I wouldn't be able to get the lens close enough and still have enough light. That's why I need to mount those on a microscope slide and look at it using this microscope. The microcrystal test, we'll talk about this more with drugs, and we also talked a little bit with the confirmatory test for blood. Those would also be done on a microscope slide, and you would use a compound microscope. Okay, now both of these, don't let the pictures deceive you. Okay, a stereo binocular microscope has two ocular lenses. Okay, it allows you to see the object in 3 dimensions because you're using both eyeballs. A compound microscope may have only one eyepiece if you're in 4th grade, or it could have 2 eyepieces. Okay, so I don't want you to look at the number of eyepieces and say, oh, that's compound or oh, that's stereo binocular. Don't look at the eyepieces. It'll just confuse you. All right, but both of these microscopes do have an eyepiece that has a magnification lens in the eyepiece. Okay, and usually the magnification in the eyepiece is something like 10 times. Okay. The second type of lens is the objective lens, and this is what I want you to look at to determine the type of microscope. Okay, notice the compound microscope, the lenses are fixed in these little 3 columns. Okay, and if you use a microscope in high school or something, you probably remember this. Okay, why are they fixed? Because the magnification is much higher and it's very sensitive it'll get out of focus if this series of lenses is not spaced exactly correct. All right, so in other words, you usually have one that might be like 4 times, one that might be like 10 times, and one that might be 40. That's what we have in our lab. Okay, but what happens is you multiply that times the 10 times eyepiece, and your total magnification for this microscope is 40, 100, and 400. Okay, that's pretty high magnification. At 400 times, you can easily see sperm cells underneath the microscope. Okay, so because these are such high magnification, that's why they're fixed, and also you click them in and they get very close again to that microscope slide. Okay, here, the objective lenses for the stereo binocular microscope, it looks like a camera lens, like a DSLR camera. All right, and usually these lenses, you can just sort of like slowly zoom in and out. It's not like click 40, click 100, click 400, you know, and there's nothing in between. This, you can sort of slowly go, and usually it's something like 1 times, and it can go up to, you know, maybe like 5 times or something. So that means your total magnification, when you multiply it by the eyepiece, would be anywhere from like 10 to 50. And these are all ballpark terms. I mean, they vary based on the microscope. But that's sort of the magnification. So it's not as high as magnification as this. But because it's lower magnification, it's not as important as far as the position of the lenses. So that allows you to sort of manually change the distance between the lenses and zoom them. All right, so again, this looks like a camera, stereo binocular microscope. Compound looks like those fixed objective lenses that are clicking. All right, here's a couple bold terms. Hey, this is good for a multiple choice question, right? If you want to measure something underneath a microscope, the length of a fiber, let's say. You could throw a ruler under there and do it, but for a compound microscope, you can't throw a ruler under it because a ruler's opaque. The light wouldn't go through it. Well, you can use a clear ruler, Dr. Linville. Yeah, you can, but the marks on that, it would be very difficult to sort of nudge it in there, because if you move the ruler just a very tiny bit, it moves a lot when it's underneath the magnification. So the solution for and you may bump your sample, The solution for this is putting the ruler in the eyepiece. So it's actually a thin disc of glass that you put in the eyepiece. So you're looking through this transparent ruler, and it's always projected on top of the image of whatever you're looking at. All right, so the ruler will have different dashes in it, but those dashes won't have numbers. It'll have sort of a conversion chart, because when you're at 10 times magnification, maybe every slot is 1 micrometer. But then when you go up to 100 times magnification, then maybe every slot is like 1 nanometer. All right, and that conversion was not done to scale, but you get the general idea, okay? The scale, the little dashes in that micrometer, the distance between those dashes changes based on the magnification. So you'd have like a conversion chart that would come with it. But you can very easily line that up, hover it over the object and measure it without nudging the object. All right, magnification is just the amount that the object is enlarged, and I've already mentioned magnification and how stereobinocular microscopes tend to have lower magnification overall when compared to compound microscopes. Working distance is that distance between the objective and the object that you're looking at. So with a microscope slide, you can get the objective lens very close to it, meaning a small working distance, but a high magnification. The stereobinocular microscope, it's different. Since you have a 3D object and you need to get that reflected light in there, the working distance tends to be larger and the magnification tends to be smaller. Okay, so in general, the smaller the working distance, the higher magnification you can go. Okay, that's it for compound versus stereobinocular. Okay, those are two different types of microscopes. Okay, here is a polarized light microscope. The two different categories of microscopes. So I want you to look at this microscope, and I want you to tell me either in the chat box or out loud at home, what category of microscope is this? Is this a type of compound microscope, or is this a type of stereobinocular microscope? And remember, don't look at the eyepieces. All right, so we have answer in, and it says compound, and that is correct. So if you said compound out loud, congratulate yourself. All right. Yeah, it's compound. Wait a minute. It has the two. No, don't look at the eyepieces. Look at these. The objective lenses, they're fixed lenses, high magnification. It's made for a microscope slide. All right. And in fact, do I have words with this polarized? Yeah. A polarized light microscope is usually used to measure optical properties of an object you can shine light through. So that would usually include glass, sometimes crystals, like in a microcrystal test for drugs or blood, and also fibers. All right, what we're looking at over here is we're looking at a synthetic fiber, I believe. And polarized light is passed through this fiber, and depending on whether the direction that the fiber is arranged in the field of view, like if it's slanted in this direction, you'll notice it sort of refracts the polarized light so it appears red and purple. But this is the same fiber as down here in B. It's rotated so it's in the other direction, and you'll notice the colors change. Now it's more of a blue and purple. All right. Well, what is if white light, just normal light, is going through a fiber, then it's going in all different directions when it hits the fiber, and it comes out in all different directions and all different wavelengths, and it looks, like white light going in and white light coming out. Okay, or maybe it takes on a certain tone that the fiber has because it's, absorbing light but allowing green light to pass through, so it looks green. But with polarized light, the difference between polarized light and normal light is you pass normal light through a polarizer. And if we think of a polarizer as sort of a disc with a bunch of tiny slits in it going in one direction. Okay. The light that comes through it is only the light that is moving where the wave is moving in the same direction as that slit. Okay. If the light, and this is, I'm very bad artist in 3D, but if it's moving from the front to back here and the slits go from left to right, then it's going to hit that polarizer and it's going to stop. It's not going to pass through. Okay. So you only get polarized light moving in one direction. I don't think Jacob asks if I assume the fibers in the picture, if it's any relation to, or wait, are you just asking about polarized and the refraction of the Pink Floyd? Yeah, with the Pink Floyd logo, that's not necessarily a polarizer. That's more a prism that takes a white light and spreads it into different colors because of the wavelength. A polarizer would be, do you guys ever go to a 3D movie and you get those 3D glasses? If you have a pair of 3D glasses around the house, and I'm also going to give you another example as well, what you'll notice is if you look at somebody else wearing 3D glasses and you close your left eye and then you close your right eye, what you're going to notice is that when you look at the other pair of glasses, one of the lenses is dark and the other is not as dark. I mean, it's still tinted, but not as dark. And then when you switch eyes, the lenses switch. And it's because in the lenses that are lighter, the polarizers are lining up, and actually the light you can see passing through both of those lenses, whereas in the dark one, they're in a different direction. All right, that might not be the best example. The other thing that I've noticed, no, Kayla, not the red and blue ones. These are like the new 3D glasses that look like dark sunglasses. Okay, because the way that they separate the light coming from the screen is, and I'm not sure exactly how this works, but it's through polarized. So each of those lenses is polarized, but it's in a different direction. All right, the other thing that you guys may have noticed is that I never realized the light coming off of my phone was going through glass that was polarized, because I wear sunglasses, which are pretty cheap, but they're polarized sunglasses, which a lot of sunglasses are. And I noticed that if I'm outside and looking at my phone in portrait mode, everything looks okay. But if I turn my phone to landscape mode, all of a sudden the screen goes black. And for a long time, I'm sitting there hitting the button going, why can't I see the screen? Why isn't it lighting up? And I realized it's because I had my sunglasses on. All right, some of you may be doing this on a daily basis and not realize what's going on. But if you have sunglasses on and your phone, you can't see it very well, try taking your sunglasses off. You may be surprised. And the reason for that is the light is coming off polarized in a certain direction. And if it's not lining up with the slits, if we want to think of it that way, in your sunglasses, then it's not going to make it through. Okay, so let's get back to the fibers. What happens is if you put polarized light through a fiber that's only moving in one direction, then the fiber sort of alters the direction that light is moving, and it may sort of refract it, the polarized light, if it hits it at a parallel, if the light is parallel to the fiber, then it may change it to where it appears a different color, in this case red or orange, versus if it's perpendicular to the light. So in both of these things, the light, we can always think of it as moving in this direction, zigzagging in this direction. So if it goes through the fiber as the light zigzagging in this direction, the fiber appears orange. If it's light's going in this direction and the fiber is in the opposite direction, then it appears blue. Oh God, Dr. Lab, in what form is this going to become a question on the quiz or exam? Well, I'm not going to ask a lot of details or give you an essay question or anything like that. But what I want you guys to know is that fibers and glass, if you look at it under a polarized light microscope, then as you rotate the fiber or rotate the glass, it can appear differently. So in other words, it may be where if you just look at two different fibers under white light, they both look green, right? But if you look at them under polarized light and rotate them, then all of a sudden they both look green on the fast axis, but one of them changes colors, as you rotate it perpendicular. So again, it just gives you more optical properties for fibers or glass. All right. Okay. Comparison microscope. This is a type of microscope. I want you to look at this comparison microscope and tell me, does it fall into the category of a compound microscope or a stereobinocular microscope? Because again, those are the categories. All right, we get a couple correct answers off the bat. Again, yeah, you're looking, don't ignore the eyepieces. You're looking down here, and it's compound because it has those fixed objectives, okay? So this would be good if you're looking at like a hair sample that's your unknown from the crime scene, and then you have your suspect's hair over here, which is your known sample you're comparing it to. You want to look at them at the same time. I think in the opening credits of one of the CSIs, they like have, you know, an image where it's a hair sample, and they're sort of like sliding it back and forth, so it looks like it's two hairs, and you can sort of see what's going on here. All right, the comparison microscope is where you're able to look at two objects that you want to compare their optical properties side by side, and you're able to see them at the same time in the field of view. All right, for the compound microscope, so this is sort of what the final product would look like. Now, I want to explain something here. This is a compound microscope. This is a bullet. This is actually used with the comparison microscope that is stereobinocular. It's important to understand. A comparison microscope can be two compound microscopes that are linked together for looking at hair and fibers, or it could be two stereobinocular microscopes hooked together for looking at bullets. All right. This is an image from that stereobinocular from a stereobinocular comparison microscope, and you'll notice that there's sort of like, you can almost see this thin crack going through it. Okay, what is actually happening here is on this side, you're looking at your unknown bullet, the back of what could be a very damaged bullet at the front, and then over here it's the known bullet. And you can see that they're side by side with just that sort of thin layer of separation. Okay, this image over here on the right is coming from the unknown bullet that's sitting down, you know, on this side of the stereobinocular microscope. There, I'll draw a bullet. And then this image right here on the left, again, is from a different bullet, the known bullet that's on underneath the other microscope. Okay, you can just look at them at the same time. Now, it used to be where a comparison microscope, the analyst would say nothing compares to a comparison microscope. There's no fancy digital imaging systems that can compare to seeing you know, both bullets under a microscope in real time. So the optical bridge is the way to go. But future changes things. So now what's going to happen? In a current comparison microscope, you're going to have a camera right here, a camera right here, and it's going to feed the images onto a computer monitor, high res, okay, where you can actually see them side by side on a computer monitor. Okay, I mean, remember, you guys are old enough to where you can remember what it was like 10 years ago with the technology, where computer screens didn't look that great. Digital cameras did not look that great, right? Okay, but now that digital imagery has gotten better and better, and the processing of computers used to look at images has gotten better and better, these comparison microscopes are almost all moving digital to where you can look at them on a computer screen. Okay, but it's still, okay, that's just taking out the eyepieces. Down here, it's still going to be the same objective lenses for a stereobinocular or compound microscope. The only difference is, instead of this big optical bridge up here, okay, it just is two cameras feeding into a computer. All right. Why even look at these fibers, and if we can't come to a definite conclusion? Well, just like with the crime scene lecture, the Tom Bosley, Scott Baio lecture, we can link objects, people, places, and things. Okay, here, a thing is a ball peen hammer, a location is a rug, and there we have a victim. This is, again, PowerPoint award-winning art here. Check that out, suspect. Can you tell? He has an eye patch. That makes him more suspicious than the victim. So if the suspect murdered the victim with a ball peen hammer on that rug, okay, in the process of committing that crime, different types of materials are going to be transferred either from the object to the victim to the location to the suspect, etc., etc. That object may have hair from the victim, hair from the suspect, fingerprints from the suspect, fibers from the rug. Okay, so an object can contain a lot of these different types of trace evidence. Okay, the rug itself may have hair fibers from the victim's clothing or the hair from the victim itself, also from the suspect. There may be chunks of metal, splinters of wood. I mean, a ball-peen hammer doesn't really shed a lot of trace evidence, but there could be something left behind on the rug. The victim could have materials from that hammer, if the hammer's not embedded into his head or anything, hair, fibers from the suspect, fibers from the rug, same thing for the suspect, okay? All right. It's the Locard exchange principle that we had before in an earlier lecture. Whenever an object or a place or a person come into contact with one another, there can be small pieces of material being transferred. And that's really what trace evidence is all about. And it just so happens there are some major categories. Like with carpet, if I got down on the floor in here and rolled around on the carpet and stood up, there would probably be a lot of carpet fibers on my shirt. There would probably be a lot of cat hair on my shirt because I'm sure there's probably some cat hair on the carpet here. If I did it in my bathroom, there would probably be some of my wife's hair on my shirt because I'm amazed by I guess I don't comb my hair often, but for people who wash their hair and dry it and comb it, like a lot of hair falls out of your head. Well, we'll get to that, in part 2 where we start talking about how hair works. All right, who's going to collect the trace evidence? Again, this is repeated a bit from a previous lecture. It's all going to depend on the agency that's doing the evidence collection. But trace evidence would be collected just like any other types of evidence. Your crime scene unit would be trained on how to identify and collect trace evidence properly. If it's found on a victim, it may be where just the entire victim gets zipped up and sent to the medical examiners, and then officers will go there and collect the trace evidence, or they may collect it from the body at the scene. So it's just like we said before. It's probably going to be a crime scene investigator, but that crime scene investigator may be a police officer, maybe a forensic scientist. If we want to throw medical examiner in there for for collecting trace evidence off of bodies, that may be another individual who collects it. All right, so if a glove has glass or fibers or blood on it, how do we want to collect this? It's probably best just collect the entire object. Similar to if we're talking about blood, you don't necessarily want to swab the blood off of this object. You want to collect everything, so you're just going to throw it all in a bag. There are some exceptions to this rule where you don't want to collect the entire object if it's extremely big, or if the trace evidence may fall off. You definitely want to make sure you're packaging it in some type of plastic envelope without any holes in it so you don't lose the trace evidence. It says trace evidence may be transferred to a different irrelevant area of object. If you're planning on proving that a person was kneeling on a rug, either when they were killed or they were, looking for something, I don't know. Then you may want to prove that there are carpet fibers like on the knees of the clothing as opposed to on other areas. So there you may have to take some caution, but that's like murder mystery stuff, not necessarily real life. Normally you just package the entire object, send it back to the lab, and then they will search for trace evidence when it gets back there. All right. You need to be careful when packaging trace evidence, and this really is true for all evidence, where you don't want to mix your known and unknown samples. And the example the book gave, especially with trace evidence where you're trying to identify whether the evidence came from a certain source. All right, if you collect the suspect's clothes that has tar on the knees of the pants and you think that tar came from the roof, all right, of the building that the person broke into, then the cops go out and they collect tar from that roof, but they throw the pants and the tar from the roof in the same bag, and maybe there's some tar on the outside of the jar that they collected it with, and all of a sudden the question becomes, well, how did the tar get on the pants? Is it because the suspect was on the roof breaking into the building, Or is it because tar got transferred from the jar of tar that you put in the same bag? All right, so this is just a little lesson. Never package known materials with evidence material. And that's true for DNA, blood, drugs, fingerprints. Well, I don't know how you'd package a person's finger in there, but anyhow, you get the general idea. All right, when it comes to collection of trace evidence, we're dealing with small objects, and we're going to go over a couple of situations where either you might not want to collect the entire object and take it back to the lab, but remember, even if the entire object is collected and transferred back to the lab, somebody at the forensic science lab needs to open up that object and find the trace evidence on it, okay, and remove it from the object. If there's a bunch of fibers on a glove, somebody back at the lab needs to open up the glove and actually pluck the fibers off of that glove. Okay, so we're going to look at 3 different ways to collect the trace evidence off of the object, whether it's at the crime scene or back at the lab. Okay, the first is the easiest, visual inspection. What I want you to understand about these things is that as we go through the 3 different methods for collection, each one collects more and more material, but each one collects more and more material that you don't want as well. Okay, so it collects more of what you want and more of what you don't want. So you have to use that to balance it. All right, if you're looking for a certain type of hair or fiber where you can easily look at the object that you're searching for, let's say you're looking for hair on a glove, like you think the glove was used to drag the victim by the hair out into the woods. All right, then you could very easily throw that glove under a spotlight, and just any hair that you see on the glove, you take a piece of forceps, you pull the hair off of the gloves, and you put it into a separate envelope. Okay? So if you're in a situation where you can find only what you want and collect only what you want, then you would use forceps. And just that's visual inspection. Look at it, collect what you want. All right. What are you going to package that hair in? Some paper envelopes have holes in them where the hair may literally fall out or start to fall off. So you usually want to use something that doesn't have any holes in it, just like a small plastic Ziploc bag. Here, we're not dealing with biological material. We don't have to worry about the DNA breaking down. So usually zipping it up in a plastic bag or putting it in a glass vial is going to be fine. Don't worry about the drug-asphalt paper there. Okay, double packaging just means that once you put it in a small object, you don't want to have a case where there's just a ton of tiny paper envelopes with stuff. You want to make sure they're properly labeled, and then maybe all of the different materials. Like if you have a glove and you're taking off blonde hair and brown hair and purple fibers, let's say, then you'll have an envelope for each of those, and then all of those can be, packaged together. All right. A tape lift. Okay, let's say that you're looking for purple fibers on a black dress. Okay, the black dress is pretty big. And even with shining a bunch of light on that black dress, it may be difficult to see the purple fibers on that dark background. So instead what you can do is you can take a tape lift, and this is just like when you're getting ready to go to the prom, and your mother says, "Jason, you look horrible," and takes that packing tape, or we had masking tape. Like packing tape didn't exist when I was in high school, I don't think. Okay, but it's like that beige masking tape, and my mom would wrap it backwards around her fingers and then would tap it on my clothing, and it would like pick up all of the lint. It's like a good old-fashioned lint brush. You know those 3M rollers, lint rollers that they make now? That originated with moms putting masking tape reverse around their hands and cleaning up their sons after they told them they looked horrible. Anyhow, okay, it's a way. If you and typically in a forensic science lab, you use a clear packing tape, okay, just like the 3M, storage tape that you use to tape up boxes when you move. You'll put that again around your hand, backwards, sticky side out, and just apply that on a certain area of the black dress. Then when you're done, you cut the tape, fold it back on itself, sticky side to sticky side, so the non-sticky sides are out. You can label it, black dress, upper left shoulder, or whatever, and then stick that in an envelope. And with that clear tape, it's very easy to throw that underneath a microscope and search for the purple fibers that you're looking for. Okay, so you're also going to collect, in addition to purple fibers, a lot of black fibers from the dress and a lot of hair from the dress and other stuff that you don't want. but it's a very good way of sort of collecting fibers from a large area, because you may be able to process the entire dress using like 20 pieces of tape, but you can very quickly look at those 20 pieces of tape underneath the microscope. Okay, vacuuming is sort of the extreme version of this. So let's say you're looking for purple fibers, but it's in the trunk of a car. Well, that's a lot bigger than the black dress. I don't know, let's say it's a big trunk. So doing it, and it's a little bit awkward to get in there and do a tape lift under the entire trunk of the car. So what you may do is use a vacuum where you vacuum small sections of the trunk, collect all of that trace evidence onto a piece of filter paper, and then you can label the filter paper. Take it back to the lab and look at it under a microscope to look for those purple fibers you're trying to find. All right. If the victim was wearing like a purple mohair sweater found and you think that the mohair sweater was at one time in the trunk of that car with the victim inside, obviously. So what you could do is vacuum again the car, and you may divide it up into 100 different sections. So you may have 100 pieces of filter paper, but you can still process that trunk, collect those 100 pieces of filter paper relatively easily, and then take them to a controlled environment where you can search for them. All right. Okay, notice with this vacuum, the big difference here, because most vacuums have filters, is that we can see this, the filter is at the very front in front of the nozzle. So as you begin vacuuming, all of the material that goes in will be collected on this piece of filter paper. Then you just take it out. Okay, you collect it, label it, put another piece of filter paper in, and then vacuum another section. All right, so vacuum a small area at a time, change your filter's frequency, and obviously you're going to put them in separate than like little plastic baggies. Or, if it's not important as far as whether you found the fibers in the front of the trunk or the back of the trunk, you could always package, like 5 different fibers together or something like that. All right. Your book refers to this as the most improperly used method, and I think there may still be a multiple choice question about this, so pay attention to this bullet. And it just emphasizes that if you just use this vacuum for something and you don't know what you're looking for, you could wind up with hundreds of filters and somebody has to go through them and search for something relevant. And if it's not properly organized, then you could just end up collecting a lot of, because you got to understand, when you're vacuuming that trunk of that car, you're not just picking up the purple filter fibers, you're picking up all of the other crap that's been in the back of that car. So you get so much junk with vacuuming, so much of the stuff you don't want, in addition to the stuff you do want, that you need to be careful when you use this vacuuming. Okay, so once we get all of this material back to the lab, what is the point of the analysis? Well, you collect this trace evidence from the crime scene or the victim or an object, so it's your evidence, and you're going to compare that to where you think it came from. All right, so here, evidence recovered from a victim would be our evidence. That would be our unknown sample. Where's my cursor here? And then you compare it. You go and collect your known sample, a rub from the suspect's van. Here, you recover soil from the suspect's shoe, so you go and collect soil from the crime scene to see if you can match it up. All right, so you just have to properly identify. I mean, you can't really do this analysis unless you have a known sample to compare it to. So it's not like you're going to get fibers, off a dead body, stick them into a magic machine, hit a button, and then it pops up. These fibers are, made by Jerry's Fiber World, and they're found in 15 cars. And here's a Google map of where all those 15 cars are right now. P.S. One of them belongs to the ex-husband of the victim. It doesn't work like that in real life. Okay. So now we go back to what I talked about at the beginning of the lecture. Since we're comparing class characteristics, that we're going to look at this more specifically in part 2, it's very rare that you can say it's a definite yes, because most trace evidence doesn't have individual characteristics. So your job as an investigator, and I believe I give better tips in part 2 of how to complete the assignment that's due this week, okay, is you want to tell the jury what you did, Okay, in other words, that don't assume, especially in the assignment that's coming up, don't assume that the jury knows everything you did. Okay, they're not reading the same story problem. You need to tell them all of the traits that you looked at and that they matched or didn't match. Okay, and then if all of them do match, you need to give them an idea of how rare those similarities are. You don't want to just say, yeah, we found the fiber matched the trunk of the car and it's found in a lot of other cars too. What is a lot of other cars? If you have the information, tell the jury that information. All right. Okay. Because if the class characteristics are the same, then you want to give the jury an idea about, again, how rare that category is. This goes back to lecture number 1 in this class. Okay. If you're comparing traits and they're the same, okay, the pencil is yellow, the evidence is yellow. Okay, how rare is that? Well, there's a lot of rare pencils. There's, 1 million yellow pencils sold in the United States or whatever. Okay, because for trace evidence, I mean, you can imagine you can get carpet fibers that are pretty rare. You can get carpet fibers that are very common, especially if it's like an older carpet fiber from some strange Oriental rug or something like that. See, I'm just trying to help you out with your mystery novels. But if class characteristics are different, like the color of a fiber can't change over time. The optical properties of glass can't change over time. It's not as though when the glass is broken, the optical property was 1.7, or the refractive index was 1.7, and then when you analyze it later, it's changed to 1.4. No, a lot of these properties of fibers and glass and soil are fixed and don't really change over time. So if you do find a difference, it is possible with trace evidence to say, yeah, it definitely did not come from the same from the same source. When I look at it, even though both these fibers look green, when I look at it under a microscope, this fiber we found on the dead body is a different shade of green, and by the way, it's polyester, than the fiber in the trunk of the car, which was bluish green and made of nylon. Could not have come from the trunk of that car. All right, that's it. So in part 2, there is going to be, be sure to watch that. I think that's where I give more tips on how to complete the assignment. And we go into the details of, okay, specifically for glass, what are the traits of glass? How do you do the analysis? For fibers, what are the traits of fibers? How to do the analysis? All right, I'm going to pause now. If anybody has any questions about this lecture, feel free to ask them now, and I will answer them on the recording, and then I'll shut off the recording. If you want to ask me about anything else, then you can do that as well. Let me double check everybody, and I believe I have everybody in the chat room already down on attendance, so you guys are free to go whenever you want to. Thanks for listening. That wasn't bad. What did I say? We'd finish up around 7:30. There will not, Jacob. Yeah, so for part 2, you'll have to watch the archive for part 2. But I think it was recorded over the summer, so it shouldn't be very, very old. Yeah, the next live, because I think next week is an off week for live lectures, so I think the next live lecture is not for 2 weeks from now. All right. Yeah, thanks everybody. All right, I'm going to go ahead